In episode 103, titled NAC Concepts, Posture Assessment, Enforcement Points, Dynamic Lists, we frame network access control as the discipline of deciding who can connect and what they can reach, because that is the simplest way to remember what network access control is trying to accomplish. Network access control, often shortened to NAC after first mention, is not just a product category. It is an access decision system that ties identity and device condition to network permissions. The exam language typically focuses on concepts like posture, enforcement, and segmentation outcomes rather than brand-specific implementation details, so the goal is to explain how the decision is made and where it is enforced. In modern hybrid environments, the risk is less about whether a device can physically connect and more about whether a device that connects is safe enough to be trusted with access to sensitive resources. When you treat network access control as an adaptive access gate for the network, the value becomes clear. It reduces blind trust in connected devices. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Posture assessment is the part of network access control that checks device state, such as patch level, presence of required security agents, configuration compliance, and sometimes encryption or endpoint health indicators. The point is not to interrogate a device endlessly, but to confirm that the device meets a minimum security bar before granting it access to higher trust network segments. Patch level matters because unpatched devices are often vulnerable to known exploits, and those exploits can turn a connected endpoint into a pivot point quickly. Agent presence matters because many organizations rely on endpoint detection and response agents, or management agents, to provide visibility and control, and a device without those agents becomes both harder to monitor and easier to misuse. Posture can also include signals like whether disk encryption is enabled or whether the device is jailbroken, depending on the environment's requirements and the level of risk tolerance. The exam expects you to understand that posture assessment is a risk signal, not a guarantee, and that it is used to decide access scope rather than to certify perfection. Enforcement points are where network access control decisions become real, and the exam often emphasizes that these points can exist at switches, wireless infrastructure, and gateways depending on how the network is built. At wired switches, enforcement can happen at the access port, controlling whether a device is placed into a particular virtual local area network, often called a VLN after first mention, or whether it is denied access entirely. On wireless networks, enforcement occurs at the access point and controller level, where devices can be placed into different wireless networks or assigned different policies based on identity and posture. At gateways, enforcement can be applied as a policy boundary where traffic must traverse a controlled choke point to reach sensitive segments, enabling segmentation outcomes even when the access layer is complex. The key concept is that network access control is not only an authentication step, but a routing and policy step, because it determines which paths a device can use after it connects. When you understand enforcement locations, you can reason about how network access control integrates into hybrid designs without assuming it must be deployed everywhere at once. Dynamic lists are the mechanism that updates permissions based on current device context, which is important because device state changes over time and static access rules age poorly. A dynamic list might reflect that a device is compliant and therefore belongs to a higher trust group, or that it is missing a required agent and therefore belongs to a restricted group. The power of dynamic assignment is that the network does not need manual intervention every time a device changes status because the access policy follows the device's current risk posture. In practice, dynamic lists can map to network segmentation constructs such as group-based policies, access control lists, and policy tags that enforce different reachability sets automatically. The exam typically expects you to recognize that dynamic assignment reduces the administrative burden and reduces the window where a risky device retains broad access simply because nobody noticed a status change. When permissions update automatically, the network becomes more resilient to drift and more responsive to risk. Using network access control to segment unmanaged or risky devices automatically is one of its most practical benefits, because unmanaged devices are common and can be high risk even when they are not malicious. Unmanaged devices include personal devices, contractor devices, and many Internet of Things devices, and they often lack consistent patching, consistent endpoint agents, and consistent configuration standards. If unmanaged devices land on the same network segments as managed endpoints, they can become lateral movement stepping stones or can be exploited as quietly persistent footholds. Network access control allows you to place these devices into restricted segments, often with limited internet access and limited internal access, reducing the blast radius if the device is compromised. This is also valuable for compliance and operational safety because it enforces policy consistently rather than relying on manual tagging or user honesty about device type. The exam framing often positions network access control as a segmentation automation tool, where risk-based access decisions are enforced at the moment of connection. Guest access models are a common network access control use case because guests must be allowed some connectivity while being isolated enough to protect internal resources. Guest access typically provides internet access and sometimes access to specific public services, while preventing any reachability to internal application networks, management networks, and sensitive data stores. Isolation can be implemented through separate network segments, captive portals, and policy-based controls that limit what destinations and protocols are allowed. The network access control system can also handle guest credentialing and expiration, ensuring that guest access is time-limited and that old guest credentials do not remain valid indefinitely. The exam expects you to understand that guest access is not just a convenience feature, it is a risk management pattern that prevents untrusted devices from entering trusted zones. When guest isolation is correct, it reduces attack surface without blocking legitimate visitor connectivity needs. A scenario that illustrates posture-driven enforcement is blocking a laptop missing a required security agent from the core network while still allowing limited remediation access. The laptop attempts to connect to the wired or wireless network, and the network access control system evaluates identity and posture, discovering that the required endpoint agent is not present or is not reporting. Instead of granting normal access, the network access control policy places the device into a restricted segment where it cannot reach sensitive internal services, but can reach remediation resources such as update servers or onboarding services. This approach protects the core network by preventing an unmonitored device from gaining broad reachability, while still supporting a path to bring the device back into compliance without manual intervention. The user may experience limited access until the agent is installed and posture becomes compliant, at which point dynamic lists can automatically promote the device to standard access. The exam tends to reward this pattern because it shows you understand graduated enforcement and risk-based segmentation rather than binary allow or deny only. It also demonstrates that network access control can support both security and user productivity when designed thoughtfully. A major pitfall is relying on media access control addresses as identity for access, often shortened to MAC addresses after first mention, because these identifiers are easy to spoof and are not a strong basis for trust. Media access control addresses can be observed on local networks and then impersonated, allowing an attacker or unauthorized device to appear as a permitted device if policy relies on that identifier alone. This pitfall also creates operational issues because media access control addresses can change with adapters, virtualization, and device replacement, leading to brittle policies that require constant manual updates. The exam expects you to recognize that strong identity in network access control should be based on authenticated identities, certificates, or other robust proofs rather than on spoofable hardware identifiers. Media access control addresses can still be used as a supplemental signal in some environments, especially for device discovery, but treating them as primary identity is weak. When you avoid this pitfall, network access control becomes a security control rather than a fragile inventory workaround. Another pitfall is creating complex policies without testing, because complexity increases the chance of misclassification and outages, especially when enforcement is strict. If posture checks are unreliable, if dynamic list updates are slow, or if policy rules overlap in confusing ways, legitimate users may be placed into restricted segments unexpectedly, causing widespread access issues. Complexity also makes troubleshooting harder because responders may not know which posture condition triggered the decision and which enforcement point applied it, leading to slow resolution and frustrated users. The exam often pushes toward incremental rollout and measured enforcement for exactly this reason, because access controls that disrupt business will be bypassed or disabled under pressure. Testing should include representative device types, guest workflows, and failure modes like agent outages, because those are the moments where policy misbehavior becomes visible. When policies are kept understandable and tested, network access control becomes predictable and sustainable. A quick win approach is to start with visibility mode before strict enforcement, because observing what would happen lets you tune posture checks and policy mapping without risking widespread disruption. Visibility mode can show which devices would be classified as unmanaged, which would fail posture, and which would be placed into restricted segments under the proposed rules. This provides an evidence-based way to adjust thresholds, fix onboarding gaps, and build user communication plans before enforcement impacts connectivity. Once visibility data is stable, enforcement can be introduced gradually, starting with higher-risk categories or less critical segments, then expanding as confidence grows. The exam often rewards this phased approach because it shows operational maturity and reduces the chance of self-inflicted outages. When you start with visibility, you also build trust because stakeholders can see that policy decisions are grounded in real device behavior rather than in assumptions. Operationally, keeping exceptions time-limited and well-documented is critical because exceptions are how good policies become permanently weakened over time. Exceptions may be necessary for legacy devices, specialized equipment, or temporary situations, but they should have explicit expiration and ownership so they are revisited and either removed or replaced with a safer solution. Documentation should capture why the exception exists, what risk it introduces, and what compensating controls are in place, because that context supports future audits and incident response. Time limits also prevent the common problem where an exception created during onboarding remains in place indefinitely, silently expanding access for a class of devices that should not be trusted. The exam expects you to recognize that exception management is part of access control governance, and that unmanaged exceptions create drift similar to legacy access control lists. When exceptions are controlled, network access control remains aligned with risk over time instead of gradually weakening. A memory anchor for network access control is assess, decide, enforce, update, review, because it captures the life cycle of how network access control works and how it stays healthy. Assess is posture evaluation and identity proofing. Decide is policy mapping that assigns the device to an access tier. And enforce is applying that decision at switches, wireless, or gateways. Update reflects dynamic lists changing permissions as device context changes, preventing drift from leaving risky devices with broad access. Review is the operational habit of validating policy effectiveness, pruning exceptions, and ensuring that classification remains accurate as device populations evolve. This anchor is useful for exam questions because it gives you a structured way to explain network access control without getting lost in vendor detail. When you can narrate the life cycle, you demonstrate understanding of both the technical and operational aspects of network access control. A useful design exercise is creating a network access control policy for employee, guest, and Internet of Things devices because it forces you to think in tiers and in enforcement outcomes. Employee devices can be required to meet posture checks, such as having required security agents and patches before receiving standard access to internal resources, with dynamic promotion and demotion based on compliance. Guest devices can be placed into isolated segments with Internet-only access and time-limited credentials, preventing reachability to internal networks while still supporting visitor connectivity. Internet of Things devices can be placed into tightly restricted segments with allow-listed destinations and limited protocols, because many such devices cannot meet typical posture requirements and should not have broad internal reachability. The policy should be tested in visibility mode first to confirm classifications match reality. Then enforcement can be phased in to minimize disruption. The exam expects you to think in these categories because they represent common device populations and common risk profiles, and network access control exists to handle them predictably. Episode 103 concludes with a practical approach. Use network access control to assess device posture, decide an access tier, enforce that decision at appropriate network points, update permissions dynamically as device context changes, and review policy and exceptions routinely. Posture assessment and dynamic lists make access adaptive, which reduces risk from unmanaged and non-compliant devices without relying on manual intervention. Guest isolation and tiered access models protect internal resources while maintaining usability for visitors and specialized device populations. Avoiding pitfalls means not relying on media access control addresses as identity and not deploying complex policies without testing, because both lead to security gaps and operational outages. The policy narration rehearsal is to take a real environment and narrate how an employee device, a guest device, and an Internet of Things device would be assessed, classified, and restricted, including how exceptions would be managed and reviewed. When you can narrate that policy clearly, you demonstrate exam-ready understanding of network access control concepts and the operational judgment needed to deploy them safely. With that mindset, network access control becomes a living access governance system rather than a brittle onboarding gate. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.